unknown function. Okay, the next one could be question number 8, which is finding the inverse of the given function. So let us start from the first one. The first one could be find the inverse of h of x equal to the cube root of x minus 3. So in order to follow or simply just to have the inverse of the given function, we have usual steps or simple around 3 or 4 steps. The first step will be letting f of x or simply the image of the arbitrary element of the x within the domain of this function to be y, so that h of x equal to this function could be taken to be y is equal to the cube root of x minus 3. Then if we try to solve for this x, we have this one that is y plus 3, that is taking this one to the left side, is equal to the cube root of x. Then taking the cube of both sides, we have y plus 3, the power of 3 is equal to x. Then replacing the variables y and that of x and taking f inverse of x for x, we have y is equal to x plus 3, the power of 3. Could be the inverse of the given function, or generally h inverse of x equal to x plus 3, the power of 3. In order to check if we need checking for this one, we know that h inverse of the composition of h inverse of x must be x. So h inverse of x is equal to the cube root of x plus 3, the power of 3 minus 3, which is equal to x plus 3 minus 3, which is what? X. So that exactly h inverse of x is equal to x plus 3, the power of 3 could be the inverse of this one, that is h of x equal to cube root of x minus 3. Similarly for b, we're asked just to find the inverse of g of x equal to the fifth root of minus x plus 2 over 2. So following the same procedure or simple step, we have g inverse of x is equal to, replace, for example, g of x by y first, and it becomes y is equal to the fifth root of minus x plus 2 over 2. Then taking the raising to the fifth power by the power of 5 is equal to minus x plus 2 over 2. And multiply both sides by 2 again, just to make this one, the denominator of this one, to be 1. We have 2 times y the power of 5 is equal to minus x plus 2. Then taking x to the left and this one to the right side, we have x is equal to 2 minus 2 times y the power of 5. Then taking f inverse of x and interchanging x and that of y, we have g inverse of x is equal to 2 minus 2 times x to the power of 5. If you need just to check, g inverse of x must be x, which is equal to the cube root of 2 minus 2x the power of 5 plus 2 over 2, which is equal to the fifth root of, just after distributing this one, if we further simplify this, the fifth root of minus 2 plus 2, this over 2, and which could be, that is 2 plus minus 3 is already 0, which we are given only, we are left only, and these two can be cancelled by this one, the fifth root of x the power of 5, which is equal to x. So exactly g inverse of x is equal to 2 minus 2x the power of 5 could be the inverse of g of x, which is given here. Question number 9. Find the range of these functions. So let us see them one by one. Find the range of g of x equal to 2x plus 1. So the range could be g of x is equal to 2x plus 1 is given. It is a linear function with slope 2, which is an increasing function. Then the domain is the set of real numbers. And so that for the range as x approaches to that of negative infinity. When x approaches negative infinity, it's image that g of x will also goes to negative infinity, and when x goes to that of a very large positive number or simply goes to infinity, g of x will also tends to infinity because this function is an increasing function with a positive slope. And it is continuous, takes on every value since it's polynomial. Hence, the range of this function that's g of x is set of real number. The next one is this rational function. The range of the rational function x plus 1 over 2x minus 1. So we are given the function f of x equal to x plus 1 over 2x minus 1. So and then solving for x in terms of y, we have y is equal to x plus 1 over 2x minus 1. We have a cross multiplication, that is y times this one, which is y into 2x minus 1 is equal to x plus 1. And taking this one to the left side, we have 2xy minus y. That's distributing this thing, we x plus 1. Then rearranging these terms, 2x minus x is equal to y plus the plus 1. We have x into 2y minus 1, which is equal to y plus 1. Then if we try to solve for x is equal to y plus 1 over 2y minus 1. Then, but this one is undefined whenever y is equal to this one, that is 1 over 2. And is at y is equal to 1 over 2, this expression or rational function is undefined. Therefore, checking for y is equal to 1 over 2 would give 2 is equal to minus 1, which is impossible. Therefore, the range of the given function, that is f, could be r without this fraction, that is 1 over 2, where this is undefined. The third one, the range of h of x equal to the square root of x plus 4 minus 3. So h of x equal to square root of x plus 4 minus 3 is given. Therefore, the domain is, that is already correct, that the radicand, that is x plus 4, needs to be non-negative, so that this must be greater than or equal to 4, and this could be satisfied whenever x is greater than or equal to minus 4. Then, and this is for all x in the domain, and the minimum value of this one could be, the minimum value of this could be, that is, the square root would be minimum whenever it is 0, so that it could be 0 whenever x is equal to minus 4. But h of minus 4 is equal to 0 minus 3, which is minus 3. Therefore, the minimum value of this functional value, the functional value of this function h of x is minus 3. At maximum, whenever x approaches infinity, that means when x gets very large positive number, its functional value, that is h of x, will tend to positive infinity. So h of x, and also, therefore, but h of x or simply x can never goes to that of negative infinity because the domain is already greater than or equal to minus 4. So that the range could be from the minimum value of this functional value, which is attained at x equal to minus 4, to positive infinity. Therefore, this is the range. Question number 10. Find the quotient and remainder of the functions given here. So let us see them one by one. Polynomial division, long division method could be applied here. When we divide x squared over x squared, that is the leading term of the denominator, by the leading term of the denominator, we have x. And if we multiply the quotient by the denominator, we have x into x plus 4, which is x squared plus 4x. And if we subtract this product from the denominator here, we have x squared minus 5x plus 8 minus this one, which is minus 9x plus 8. So they hit the first remainder, which is obtained at the first step. Then next, we have to divide this one again by the denominator, the leading coefficient of the term of this one, that is minus 9x over x is minus 9. So this is the first quotient. And if we multiply this one, the quotient by and the denominator by this one, that's minus 9, we have this minus 9x minus 36. And let's subtract this one from minus 9x plus 8 minus of minus 9x minus 36, which is 44. Therefore, this is really the remainder, and the quotient could be x minus 9. Therefore, if we check this, that is by using that of polynomial division algorithm, they hit the quotient, this is the denominator, and this one is the remainder. Then when we multiply these two, we have x squared minus 5x minus 36. If we add the remainder, we have x squared minus 5x plus 8, which is the given function. Similarly, the second one, to execute minus 7x squared plus x plus 4 divided by x minus 4, that is, let's find the remainder and the quotient, which is obtained by dividing this cubic polynomial function by x minus 4. Let's divide the usual, that is long division method, to execute by x. We have 2x squared. And let's multiply the denominator by 2x squared and subtract from the denominator, so that we have this one, the product. And let's subtract to execute minus 7x squared minus to execute minus x squared, which is x squared, and bring down x, so that x squared plus x, and divide the first one, that's simply this difference, by again this one, the leading term of the denominator, which is x, we have x here. Then multiply the denominator by x, we have x squared minus 4x. So that if we subtract this product, the product, that is x squared minus 4x from x squared plus x, we have 5x. Then bringing down 4, and 5x plus 4 could be again divisible, because we have a linear denominator, so that it becomes 5. And then if we multiply the denominator by the quotient, which is obtained at this step, we have 5x minus 20, and let's subtract this product from 5x plus 4, which is obtained here. Then the difference could be 24, so that this is exactly the remainder, which is constant. Therefore, the quotient could be 2x squared, which is obtained in the first step, x, which is obtained in the second step, and 5, which is obtained at this step. And the remainder could be 24. Therefore, this is the last answer for this question. Similarly, the next one, that is question number 10c, 1 minus x squared over x minus 1. We have rewrite the numerator first, 1 minus x squared, as the negative of x squared minus this one, which is a simplification. We have this thing, and then cancelling this one, that is x minus 1, x minus 1. We have minus of x plus 1, which is minus x minus 1, distributing this 1 minus 1 over x plus 1. Therefore, the quotient here is minus x minus 1, and the remainder is already 0. So that's the answer, which is obtained by simplification. Question number 11. If p of 4 is equal to 0 and p of x is given to be this cubic polynomial function, we're asked just to find the remaining zeros. We know that this is at degree 3, so that the polynomial function will have 4 either distinct or roots with some multiplicities. But what we are given here is the one of the possible roots of this polynomial function is that is 4, because p of 4 is equal to 4, so that 4 is the 0 of this polynomial function. And using the factor theorem, if p of 4 is equal to 0, x minus 4 is one of the possible linear factors of this polynomial function. Therefore, they hit the factor, and then the quotient obtained when p of x is divided by x minus 4 could be, that is already the remainder is 0. We have 2x squared minus 3x minus 2. You can check it. That means this quadratic equation could be obtained by dividing this cubic polynomial function by its factor, that is x minus 4. So that p of x can be expressed as x minus 4 times 2x squared minus 3x minus 2. And again, when we try to factorize this one, that's simply the quadratic expression, and that is the quotient which is obtained there, and that means 2x cubed and 2x squared minus 3x plus 2 could be factorized as 2x plus 1 times x minus 2. So that fully the polynomial function p of x will be factorized as x minus 4, 2x plus 1 and x minus 2. Therefore, the zeros of the polynomial function could be the zeros of each linear factor, so that the zeros could be x equal to 4, which is obtained from x equal to 4, x minus 4 is equal to 0. When we take 2x plus 1 is equal to 0, we can obtain x equal to negative 1 over 2. When we take or assume x minus 2 is equal to 0, x must be 2, so that 4 to end negative 1 over 2 are said to be the zeros of the given polynomial function. Therefore, 2 and negative 1 over 2 are the other zeros of the polynomial function other than 4. And next, we are also asked just to find the remaining zeros given given that 2 minus 3i is the root of this cubic polynomial function again. We know that one of the possible roots of this polynomial function is given to be the complex number 2 minus 3i, so that by using that of complex conjugate theorem, if this complex number is the root of this polynomial function, its complex conjugate, which is 2 plus 3i, must also be the root of the same polynomial function. So we are left only one root, that is 2 of the roots of the given polynomial function are complex, which are one is the complex conjugate of the other. Is that they are real coefficients or coefficient roots come in conjugate pairs, so that if 2 minus 3i is the root, then its complex conjugate 2 plus 3i must also be the root of the polynomial function. So let the third root be r. Then, by using that of sum of roots formula, 4x cubed plus bx squared plus 3x plus d, the sum of roots is equal to minus p over a, which is minus p over a, which is the term of this one, the coefficient of x squared and the coefficient of x cubed. That means, so that in this case, we have a is equal to 2, b is equal to minus 5, so that the sum of these two plus r is equal to minus of minus 5 over 2, which is 5 over 2. And the sum of these two could be 2 minus 3i plus 2 plus 3i could be minus 3i plus 3i will be 0, 2 plus 2 will be 4, so that we are left only 4 plus r is equal to 5 over 2. So that the difference could be taking 4 to the right side, 5 over 2 minus 4, which is equal to 5 over 2 times minus 8 over 2, which is equal to negative 3 over 2. Therefore, 2 minus 3i, 2 plus 3i, and negative 3 over 2 are said to be the zeros of the given polynomial function, so that the others or the remaining zeros of the given polynomial function other than 2 minus 3i could be 2 plus 3i, which is the complex conjugate of this complex number, and negative 3 over 2. Generally, for any polynomial function, p of x is equal to n times x to the power of n plus this one, that is general formula. Then we have if r1, r2 up to rn are its roots, and then the sum of the roots of this polynomial function could be the negative of n. It is not n, rather, sorry, it is not n, rather it must be n minus 1. This is not here. N minus 1, n minus 1 over n. Okay, this is the generalization. The next one would be, that is simply question number 11C. We have, or simply we are given a polynomial with roots 1, 2, 3 with multiplicities 3 to 1. We are asked just to find a polynomial in terms of a polynomial with whose roots are 1, 2, and 3 with their corresponding multiplicities. So just to do this, we have multiplicity. Just let us say something about multiplicity with roots with multiplicity. M is said to be a multiplicity, or simply R is said to be the root of the given polynomial function with multiplicity m whenever x minus r, the power of m, is the factor of the given polynomial function. That means whenever x minus r, the power of m, is the factor of the given polynomial function, this real number that is r is said to be, or a complex number even, is said to be the root of the given polynomial function with multiplicity this times, that is m times. Therefore, when we apply this idea for obtaining the polynomial, the expected polynomial with these roots with their corresponding multiplicities, we have 1 is the root of the given polynomial function with multiplicity 3 times. If we assume that this one is respectively, so that x minus 1 the power of 3 must be the factor of the polynomial function. Similarly, 2 is also the root with multiplicity 2, so that x minus 2 the power of 2 must be the factor of the other possible factor of the polynomial function. And lastly, 3 is the root of the given polynomial function with multiplicity 1, so that x minus 3 is the factor of the polynomial function. Therefore, when we multiply all the factors here, we have f of x is equal to, if f of x is the given polynomial, x minus 1 the power of 3 times x minus the power of 2 times x minus 3, which is equal to this polynomial function. And one thing that you should never forget, or simply should remember here, is that the degree of the given polynomial function here is 6. And this 6 is simply directly the sum of the multiplicities of the roots of the given polynomial function. That is, all the multiplicities of all the roots of the given polynomial function, which is 2 plus 2 plus 1, that is exactly 6. Next question, number 12. That is question number 12 will be find rational roots, and just sketching the graph of the given function. Let us see the first one. The first polynomial function is f of x is equal to x cubed minus 4x squared minus 7x plus 2 is given. So that the rational roots of the given polynomial function is that when we apply rational root test here, if a certain rational number p over q is the root of the given polynomial function, the denominator, that is p, must be the factor of the constant term, which is 10, and q must be the possible factor of the leading coefficient, in this case that is 1. So that the possible roots of this one are, we know that the factors of the constant term, that is the expected denominator for the rational number, could be plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10 itself. Similarly, the possible roots of, factors of the constant term, that is 1, will be only plus or minus 1. Therefore, when we combine this one with respect to, that is, the factors of 10 with the factors of this one, that's simply 1. Whenever the factors of 1 are possibly denominators and factors of 10 are denominators, we have only this one. Therefore, all the rational roots of this polynomial function cannot be out of these numbers. So in order to distinguish which rational numbers are roots of this one, we have to check each of these numbers by substituting in the place of x here, and we have to check whether they can make the polynomial function that is f of x to be there or not. For example, if we test for x equal to 1, f of 1 is equal to, if we substitute 1 here, we have 1 minus 4 minus 7 plus 10, which is equal to 0. So that one of the possible rational root of this polynomial function is 1. Then in order to check or simply find the other, if you take 2, for example, f of 2 is equal to the power of 3, which is 8. 2 squared, that is 4 times 4 is minus 16. 2 times this one is minus 14, which is different from that of 0, so that 2 cannot be the 0 of this polynomial function. Let us check for minus 2, that is f of minus 2 is equal to minus to the power of 3, which is minus 8, minus 2 squared times minus 4, that is negative 16. Negative 2 times this one is positive 14, plus this one could be, this is minus 24, plus 24, that is 0. So that the second rational root of this polynomial, cubic polynomial function is negative 2. Similarly for 5, f of 5 is also 0, therefore all the rational roots of these polynomial functions are rational, and these are, that is 1, negative 2, and 5. Hence, f of x has 3 distinct rational roots, and the roots are minus 2, 1, and 5. Or even using factorization, factor theorem and combination of remainder theorem, we can easily obtain the root of the given polynomial function. Then for the quadratic expression, that is, if we factorization, that means because already one of the possible rational root of the given polynomial function is this one, that's simply x minus x, y 1, so that x minus 1 is factor. So when f of x is divided by x minus 1, the quotient is x squared minus 3x minus 10. Again, if we factorize x squared minus 3x plus 2, it becomes x minus 5 plus times x plus 5. So that fully the factorized form of f of x could be x minus 1 times x minus 5 times x plus 2, so that the roots are 1, 5, and negative 2, as it is obtained previously. Then just to check, sketch the rough graph of the given polynomial function, we need to know, or simply just to have, the degree 3 with positive leading coefficient, so that it could be an increasing. The roots are minus 2, 1, 5, which are the expected x-intercept of the graph of the given function. That means the y-intercept whenever x is 0, that is f of 0 is equal to, that is 10. And also the x-axis at each root, that's simply minus 2, 0, 1, 0, and 5, 0 are the x-intercepts. So the rough graph of the given polynomial function looks like this one. The x-intercept is minus 2, 0, minus 2 is 0, 1, 0, 1 is one of the second root of the given polynomial function, and 3, 0. And it has 2 turning points, because the curve of a polynomial function, if the degree is n, at most the graph will have n minus 1 number of turning points. And when we assume or simply take x is a very large positive number, so that its functional value will also goes to positive infinity. When x is a very small negative number with a very large absolute value, so that its functional value will decrease indefinitely without any bound. Therefore, roughly the graph of the given function looks like this. Okay, the next one, that is question number B. F of x is again cubic polynomial function with these terms. Therefore, the possible roots for this one is again, the constant term is here 1, that is, but the possible factors of this one, that is 1 is plus or minus 1. And the leading coefficient is 6, so that the possible factors are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So when we combine or simply obtain a fraction or simple rational number by taking plus or minus to be the expected denominator for the rational number and the factors of this one to be the denominator, we have this one. Therefore, if all the roots of these polynomial functions are rationals, so that the roots can never be out of these rational numbers. Therefore, in order to distinguish which rational number is the root of the given polynomial function, let us test for x equal to 2. We know that f of 2 is, if we substitute 2 here, we have 3 over 4 plus 1 over 4 minus 2 plus 1, which is already 0. Therefore, this one that is 1 over 2 is one of the possible rational root of this polynomial function. If 1 over 2 is it is a rational root, hence using the factor theorem, we know that x minus 1 over 2 must be its factor, so that when we divide this trinomial or simply the cubic polynomial function by 2x minus 1, which is one of the possible factor of this polynomial function, we have the quotient 2x squared plus 2x minus 2. And the quotient, that's simply this quotient 3x squared plus 2x minus 1 can be also factorized as 3x minus 1 times x plus 2. So f of x can be fully factorized as this one, that is 2x minus 1 times 3x minus 1 plus x plus 1, so that from each the roots of its linear factors we can determine the root of the given polynomial function. Therefore, the roots are 1 over 2, which is the 0 of 2x minus 1, 1 over 3, which is the 0 of the second factor 3x minus 1, and minus 1, which is the factor of the last linear factor, which is x minus 1. To sketch the graph, the degree is the usual one, that's simply 3 with positive leading coefficient. The roots are minus 1, 1 over 3, and 1 over 2, which are the expected x-intercept of the graph of the given function. The y-intercept is it's a point at which f of x is 0, so that f of 0 is 1, 0. Therefore 0, 1 it is y-intercept. And when we put this information on the Cartesian coordinate system, the graph will look like this one. The y-intercept is this one, that's simply 0, 1. And the x-intercepts are 3, which are the zeros of the given polynomial function, which are minus 1, 1 over 3, and I think 1 over 10, yeah, 1 minus 1, 1 over 3, and 1 over 2. 1 over 3 and 1 over 2, so that they hit the graph. And we have seen previously, it is also the indices are increasing, so that when x gets a very large positive number, its functional value will also increase in the upward direction without any bound. The negative part, when x gets a very small negative number but with very large absolute value, so it goes down like this. So the graph is this one. Next, to execute minus 5x squared minus 28x plus 15. Possible roots are this one, which is the combination of the possible factors of 15 and possible factors of 2. So that if we check for x equal to 5, it is already 0, so that 5 is one of the possible rational root of this polynomial function. Therefore, if we apply a factor theorem, f of x can be, that is, if 5 is the root of this polynomial function, x minus 5 must be this factor. If we divide this one by x minus 5, so f of x can be written in this pattern, that is the quotient which is obtained by dividing this cubic polynomial function by the first linear factor, that is x minus 5. But 2x squared plus 5x minus 3 can also be factorized as 2x minus 1 plus x, 2x minus 1 times x plus 3. Then totally the function f of x can be expressed or factorized as x minus 5 times 2x minus 1 times x plus 3. Then from the linear factors, the roots of the given polynomial function are 5, 1 over 2, and minus 3. If you want to check this one within the possible roots of there, everything will be here. That is 5 is here, 1 over 2 is here. I think the next one could be, that is negative 3, which is negative 3, which is around here. That's simply this one. Therefore, this is what rational root test is. And when we proceed to the graph of the given polynomial function, the degree is 3 again, which is positive leading coefficient again. The roots are this one, which are the expected x-intercepts. The y-intercept is obtained when x is equal to 0, which is f of 0 is equal to 15. Therefore 0, 15 will be this y-intercept. Then the graph roughly could look like this one. This is the y-intercept 0, 15. This is minus 3, which is the first 0. 1 over 2, 0. The second root end, third rational root would be 5, 0, which is the x-intercept of the graph. So the ends of the graph are increasing, that is in the upward direction in the right side, and goes in the down in the negative direction, the left side. Question number 13. Just analyze and sketch the graph of these rational functions. So let us try to see one by one. We know that in order to graph the graph of every rational function, we have to know or simply know first the basic components or simply procedures. First, we have to determine its domain, and we have to fix holes if there are, and vertical asymptotes, or simply general asymptotes. The vertical asymptote here is x equal to 3. We know that x equal to 3 is said to be the vertical asymptote of this one whenever 3 is not within the domain of the given function, and if it is not removable or simply if it is within there, so that the vertical line which passes through this point, that is x equal to 3, is said to be the vertical asymptote of the graph of this rational function. And horizontal asymptote depends on the degree of the numerator and the denominator. We know that here the degree of the numerator is 0 and the degree of the denominator is 1, so that in this case the line that is y is equal to 0 or the x-axis could be taken or considered as the horizontal asymptote for the graph of this rational function. But whenever the graph of the degree of the numerator is exactly equal with that of the degree of the denominator, the horizontal asymptote could be the quotient of, that is the vertical line which passes through the quotient of the leading coefficients of the numerator and the denominator. They hit the possibility where the given rational function has a horizontal asymptote. Therefore, the x-intercept could be, there is no x-intercept because whenever f of x is equal to 0, we have a false statement that simply 0 is equal to 4. Therefore, the graph can never intersect the x-axis because already the x-axis, that is the horizontal axis y is equal to 0, is considered or simply calculated to be the horizontal asymptote. The y-intercept could be whenever x is equal to 0. When x is equal to 0, we have negative 4 over 3. Therefore, 0, negative 4 over 3 would be the y-intercept. And if we combine this one, that is, it is a hyperbola. The vertical asymptote is this one. Horizontal asymptote is the x-axis, which is y is equal to 0. The y-intercept is 0, negative 4 over 3. Quadrants are the first quadrant and the second, the fourth quadrant. Therefore, the graph looks like this one. This is the vertical axis, the vertical line that is x equal to 0, which is the vertical asymptote, and the x-axis y is equal to 0 is the horizontal asymptote. Here, the property of the graph near the vertical axis is that when x approaches this one that's simply 3 from the right side, the functional value of the given function will tend to the very large positive number, that is to the positive part. So that this will determine the property of the graph of the given function. Then when x goes to that of a very large positive number, the graph will approach the horizontal axis, that is the x-axis, but it may never intersect or simply touch the horizontal asymptote. Similarly to the left side of the vertical asymptote, when x approaches 3 to the left or simply from the left side, the functional value of the given function or simply f of x will tends to that of very small negative number, that's simply down. And when x goes to that of negative infinity, so that the functional value will approaches the given horizontal asymptote or the x-axis from below. So the graph of the given function will looks like this. And then a hyperbola, which is found in the first quadrant, and for first and around for the quadrant. Okay, the next one could be this one, that's question number 13b. F of x given by this rational function. So first, let's factorize first. F of x denominator could be factorized as, that is trying to finding the two real numbers whose sum is 7 and whose product is 12, that is 3 and 4, so that x squared plus 7, x plus 12 could be factorized as x plus 3 times x plus 4. And the denominator, that is, if we factor out 2 or minus 2 at the common factor first, it could be x squared minus plus x minus 6. And the factorized form of x squared plus x minus 6 would be x plus 3 times x minus 2. Then we have similar factors here, x plus 3, x plus 3, so that they can be cancelled. But in this case, the domain is should be restricted first, that is x must be different from that of minus 3 and positive 2. So at x equal to minus 3, because the common factors can be cancelled, therefore x equal to negative 3 cannot be a vertical asymptote, rather we will put a hole there, a hole at x equal to minus 3 at the simplified form. Then vertical asymptote is only this one, which is it is irremovable, that is x equal to 2 is a vertical asymptote. And the horizontal asymptote could be, since the degree of the numerator and the denominator are equal, that is simply 2, so that the horizontal asymptote could be the line which passes through the quotient of the leading coefficient of these two, that is 1 in negative 2, which is negative 1 over 2. Therefore, the information for the graph of this rational function could be, we have the x-intercept, that is the denominator is equal to 0, x equal to minus 4, not minus 3, since we have a hole here. And the y-intercept is whenever x equal to 0, it becomes 12 over 12, but that is simply 1. So that 0, 1 will be this y-intercept. And the whole at x equal to 3, using the simplified form, the point that we put with the whole could be f simplified could be, that is when x minus, x plus 3 is removed or cancelled, we have this one, so that f of minus 3 at the simplified form will be minus 10. Therefore, at minus 3, 1 over 10, there is a hole for the graph of the given function. Then sketching the rational function with hole, vertical asymptote at 2, horizontal asymptote at this could looks like this. They hit the vertical asymptote. The horizontal asymptote is this one, the dotted line, the red dotted line with y is equal to negative 1 over 2. And they hit the x-intercept, which is minus 4, 0. The y-intercept is 0, 1. so that the property of the graph near the vertical asymptote x equal to 2 will be, from the right, the graph approaches the vertical asymptote and it approaches the horizontal asymptote from below. Similarly, from the left side of the vertical asymptote, when x approaches the vertical asymptote x equal to 2, from the left side, its functional value will increase indefinitely. And when x gets a very small negative number, that means x tends to negative, so that the graph will intersect the x-axis at -4, 0, and it approaches the horizontal asymptote, that is y is equal to -1/2 from above. And there is also a hole here, that is this hole, that's simply this one, which is obtained at -3 and -1/10, I think -1/10, so that this is the hole. Therefore, this is the rough sketch or simply graph of x squared plus 7x plus 12 over -2x squared minus 2x plus 12. The last one could be minus rational function minus 3x plus 12 over x squared minus 3x minus 2. Here, first, let's factorize again. F of x equal to -3 into x minus 4, and the factorized form of x squared minus 3x minus 4 could be x minus 4 times x plus 4. So we have x minus 4, we have x minus 4, they can be cancelled. Therefore, at x equal to -4, the graph will have a hole like that of the previous one. So the domain first, x must be different from that of 4 and -1. And there is a hole at x equal to 4 because it is removable. A common factor can be cancelled. Vertical asymptote is x equal to -1. That is the point at which the function is undefined. And the horizontal asymptote could be, since the degree of the denominator is less than that of the degree of the denominator, so that the horizontal axis, which is y is equal to 0, or the x-axis could be the horizontal asymptote for the graph of this rational function. Then the information for the graph of this function could be the x-intercept would be x equal to 4, but that is a hole. So the graph doesn't intersect the horizontal axis because already the horizontal axis or the x-axis is a horizontal asymptote for the graph. The y-intercept is f of 0, which is equal to 12 over -4, which is -3. Therefore, the graph intersected the the vertical axis at 0, -3. There is a hole at 4. Then, in order to specifically put the point, we have to take the simplified form of the given function. So the simplified form is -3 over x plus 1. Therefore, the functional value at 4 for this one could be -3 over 5. Therefore, the whole of the graph will be 4 with -3 over 5. Then the rough sketch of this graph, this rational function with this information, with hole at -3 over 5, vertical asymptote at 1, and horizontal asymptote at 0, or simply x-axis could be this one. That means the vertical asymptote, x equal to -1. The horizontal asymptote, that is y is equal to 0, or the x-axis itself. And the property of the graph of this function near to the vertical asymptote could be, from the left side, when x approaches to, -1, that is the vertical asymptote from the left side, it goes in the upward direction, and the graph approaches the horizontal axis, or simply the horizontal asymptote from above. That means when x gets a very small negative number, the graph approaches the x-axis. And from the right side of the vertical asymptote, when x approaches from the right side, x will approach or simply tends to that of -infinity. And when x approaches or simply gets a very large positive number, its functional value will, or simply graph will approach the x-axis or the horizontal asymptote from below, so that roughly the graph of the given function looks like this. that is all what I have for today. Next, we'll meet by other questions like this the next time. Thank you for watching. Don't forget just to subscribe this channel for more.